Hello and welcome to another video. In this video we're going to be working on number of steps to reduce a number in binary representation to 1. And in this one you're given the binary representation of an integer in a string and you want to return the number of steps to reduce it to 1 under the following rules. If it's even, you have to divide by 2, and if it's odd, you have to add 1. It's guaranteed that you can always reach it for all these test cases. So in this first example you have the number 13 and you first add 1. So you get 14, then you have to divide, so you get 7, then you have to add, then you divide. So it's 6. 10 corresponds to 2, so you just divide by 2. And then 1, you're already done. So basically we have to look at two things, and we have to try to figure out what a binary number does when you do this. Divide by 2, add 1. So let's take a look at the first one. So what happens if you take a binary number and divide by 2? Well, first of all, if a binary number ends with a 1, it's odd, so you can't divide by 2 because you wouldn't get an integer. So let's say we have some even number like this. So this represents 6. So when you divide a binary number by 2, it's the same thing as dividing a decimal number by 10. And if you take a decimal number and divide by 10, let's just say we have like 150, if you want an actual integer, like what happens here? You just pop off the last 0 and you get 15. And so here, same exact thing. You can only divide numbers that end with a 0. Similarly, the same thing for a decimal number. In order to get a whole number, if you want to divide by 10, you have to divide, it has to be a 0, so this is the same thing. So this means it's even. So this means it's an even number, just like here it means this is numbers divisible by 10. So when you divide by 2, all you do is you just get rid of this, and this is what you have. So this is 3. So that's what it is for a binary number divided by 2. Pretty easy. It has to be even. How do we check if it's even? The last bit has to be a 0. And if the last bit is a 0, we just get rid of it and then we're done. Now what about add 1? So there's a couple cases here. So let's take a look at all of them. So let's say we have this. Case number 1. If we add a 1 here, basically what's going to happen, it's the same thing as adding 10 to a decimal number. Actually, would it be the same as adding 10? No, it would be the same thing as adding 5 to a decimal number that ends with a 5. So if you have something like this, plus 5. So essentially what's going to happen here is this last bit will become a 0, and then you'll have a carry. And it's the same thing for this. So if I do 0, 0, 1, plus 1, I get 1, or I get 0, then I carry 1 over here, and then I get a 0 here. So that's one case. Now, if I have a 0 bit, so basically you're never going to be adding, you're never going to be adding to a 0, but let's take a look at one more example, and this is the one that matters. So if you have this, now what's going to happen here is this last bit will still be 0, but then you're carrying the 1 again, and then you're going to have to add the 1 over here. And then imagine if you have something like this. If you add 1, this carry is going to propagate over, right? It's the same thing as doing like imagine if you have like 9, 9, 9, 9, 9, and 5 plus 5, right? This will propagate over. So you don't really want to do that because that will take too long. But what you can do is you can say, okay, when I add a 1, then I know for sure that, let's just do like a generic case, right? So when I have an odd number, add 1, then the last bit becomes 0, and I have a carry, right? Similarly, like, it doesn't really matter. Like, if I have this plus 5, I will have a 0 at the end, and I will carry a 10. And if I have this, I will still have a 0 at the end, and I will carry a 10. So instead of propagating, we'll just say, like, we're going to carry a 10. So that's kind of the same thing here. We're only going to be adding to odd numbers, and so the last bit will become 0, and we'll have a carry. So the simplest case of, let's just say we have a power of 2. So any number with a 1 and a bunch of zeros is just a power of 2. Kind of like in a decimal number, any 1 with a bunch of zeros is a power of 10. Same thing for powers of 2. So this is pretty easy. What we're going to do is it's always going to be even, so we just divide, and we're done. Also notice that for these numbers, all of these numbers will start with a 1. So what we need to do is we need to just like handle all the bits until we have the 1 left over. So, like I said, if we had this, then it's pretty easy. We just divide 5 times. But now let's look at like a bunch of other cases. Let's just take a look at like a big example and add these things. So essentially we're going to have these situations. And then when we have a carry, so if we have a carry bit, so that's the last thing, is let's say I have something like this and I add 1. I'm going to have a carry, right? So I'm going to have a carry of 1. Then this last bit will become a 0. Then I'm going to divide. But then this number, I'm going to have to add 1 to it again because I had that carry. So basically you're saying it's the same thing as this. You know, if I have like 995 plus 5, I will get this will become a 0. Then I will carry a 10. Then when I divide by 10, I get 99. And then I will have to add that like extra 10, which is just the 1. So hopefully that makes sense. So essentially the one that you carry is going to be the one that you're adding to the next number after you divide by 2. So let's take a look at a big example now, knowing all these things. And let's just figure out what's going to happen. So obviously the carry in the beginning will start as 0. And also we basically have one of two cases. If the number is odd, we will have to make it even and then divide. And if the number is even, we just do a divide. So to get rid of a bit, we'll either take one operation or two, but then we'll have to figure out like what the carry is as well. So let's walk through this whole thing. So our carry will start off as 0. And our result will start off as 0. So in the beginning, we have an odd number, right? Because we know the last bit is 1. So we're going to say, okay, so in order to do this, we have to add 1. So then our carry will become 1. And then we just have to get rid of this number, right? So we add 1, which will basically be turning this into a 0 and then adding 1 over here. But we're not going to add the 1. We're just going to say we're storing it, and then we'll add it as we process that number. So then essentially we're just getting rid of this guy. And that was 2 operations because we had to add and divide. Now our number is 0, but we have a carry, so this number is actually a 1. And so we have a 1. So what do we have to do? Well, we're going to add 1 again, right? So our carry, so this is the case, if I do 1 plus 1, this will turn into a 0, and then I have another carry. So the carry will stay 1, and now I will divide. So get rid of that. That was 2 more operations. Because our number was odd, we had to add 1 and turn to a 0, and then we still have a carry. Okay, now we're over here. So our number is 1, but we have to add the carry. So our number is actually 0 here. And our carry is 1, right? Because we did 1 plus 1. So our carry stays 1. And this number is a 0, so we don't have to like add anymore. When we're adding the carry, like that we're not actually adding the carry. Like we're not adding a new number. It's just that carry is carried over, right? It's kind of like the 999 plus 5. We carry the 10. We're not like adding a 10 again or something. So essentially this number is 0. So it's even. The carry is 1 because we had 1 plus 1. And then we don't have to add anymore. We can just divide. So divide, and that only takes 1 operation. Now over here, so we have to do 1 plus 1. So our true number here is a 0 with a carry of 1. And so that since our number is 0, we don't have to do the add operation. So we just do a divide. So this is just 1. So we have 6. Okay, now here our true number is a 1 because we had a carry. Now our carry becomes a 0, right? Because carry is basically like the same kind of thing for tens. In order to have a carry for decimal, your number has to be bigger than 10. So in order to have a carry here, your number has to be 2 or bigger. So when we do the 0 plus 1, we will only get 1, so there is nothing to carry. So this will just be a 1, the carry will be nothing. And now we have to figure out what to do here. So this number is odd. So because this number is odd, we have to add 1. So when we add 1 here, this will turn into a 0, and now we have a carry again. And we will also divide, so that was 2 operations. Hopefully I didn't screw any of this up, but you kind of get the idea. You basically store the carry bit, you add the carry bit to your current bit, and you check, is that result 2 or more? I guess it can't be more than 2. So if that result is 2, then I have a carry, and then this becomes, so if this is a 2, it becomes 0. If it's a 1, it stays 1, right? Because the same thing here, like if you have the 995 plus 5, this thing will turn into a 0. Okay, so now we're over here. Hope I did that right. Maybe I screwed something up, but essentially this is the same thing. Okay, so we have a 0. Our carry bit was a 1, so our true number here is a 1. And our carry is now 0, because 0 plus 1 is 1. There's nothing to carry. Okay, we have odd again. So if we have odd, we have to add 1, which will give us a carry. And then that'll turn this into a 0. We'll have the carry, and then we have to divide. So it's 2 more operations. Okay, now here, our number is 1, our carry is 1, so our true number is a 0. And our carry stays 1. So if our true number is a 0, all we have to do is just divide. So we will just divide, so that's only 1 operation, so we have 11 here. Then our true number here is a 1, and our carry is a 0 after adding. Then since it's odd, we have to add 1, so we will add 1, and then we will make this carry a 1. So this is 2 operations, add 1 and divide, so 13 total. Now here, our true number is a 1 because it's 0 plus the carry. So it's always 0 plus the carry, or the number plus the carry. Our carry turns into a 0. And then, so this was 2 operations, right? We had to add 1 and divide. And then finally here, we're done. So we have a 1. So we're done. Now, you can also have a case here where you have a, like imagine you have a, you're always going to have a 1 in the start, but if you have a 1 here and you also had a carry, so imagine if the carry was here, then what would happen here is this 1, like this is always going to be a 1. The first digit is always going to be a 1, but if your carry is a 1, then what will happen is this will turn into a 0 and you'll have another carry, so it'll be this, which means you then have to do 1 more operation to divide by 2. So your number at the end will either be 1, in which case you're done, or it will be 1, 0, which means you have to divide by 2. So whatever result we get, once we have, we're not going to process the last number, but we're going to turn this result plus the carry. So if the carry is a 1 at the end, that means our true number is 1, 0, which means we have to do 1 more divide. If our carry is a 0, that means our true number is a 1, and we're done. So hopefully that makes sense. For these operations for bits. If it doesn't, just like go through a bit number, maybe convert it to decimal. So like for all this whole thing I did, right? Like what's the decimal number for this thing? You know, maybe you can do like a binary to integer converter, take this whole thing, turn it into a decimal number, and then like write out the decimal number the whole time and compare it to the binary number the whole time, and then it'll make more sense. So it's a little bit confusing, but hopefully that makes sense. Essentially, we're just keeping track of the carry bit because anytime we add 1 plus 1, this becomes a 0, and we're carrying to the next bit over here. And if we do a 0 plus 1, then we get a 1, and there is no carry. If we do a 1 plus 0, we get a 1, there is no carry. So the only time there's a carry is a 1 plus 1. And basically what happens a lot is your number will be a 1, and then you'll have to add 1 again because it'll be odd, and then you'll get a 0, and then you'll get the carry that'll go to the next bit. So that's what we're going to do. So we're going to have a couple cases here. So first we'll have a result, and we're going to process this string backwards, right? Because this is a 0 bit, 1 bit, and so on, and we're not going to process this bit because this will always be a 1. We're just going to check if there's a carry at the end. If there's a carry at the end, then we need to do 1 more operation because our true number is this, and we need to get rid of that. Okay, so our result is 0, our carry is 0. That's all we need, I think. So now we need to process the string backwards. So for int I equals s length minus 1. We don't care about the first number because that'll always be a 1, so I is greater than 0. Okay. So we're going to first get like what's our true number here, right? And our true number is whatever this was plus the carry. So we'll say int cur equals, and I talked about why this happens before. Essentially, you can do character at I. This will give you an ASCII value, and in order to get the number, it's either going to be a 1 or 0. You can't just convert that to an integer because that'll be like 50 or 60 or whatever. You have to actually subtract this, and that will kind of offset it because this is 0 because it'll be like some ASCII value minus itself, and this is 1 because this value is 1 more than this value. So imagine if this is like 60 or whatever, and this is 59. You can look up an ASCII table for the exact thing, but that's why you do it. Okay, so we get this plus our carry. That's like our true digit here. And then we have a couple cases. So if cur equals 2, which it can be, right? Because if it's like 1 plus 1, right? If this number was a 1 and we added a 1, then this becomes 0. So this is even, and we have a carry. So let's do that. So if it's even and there's a carry, then then we only have to do a divide, and our carry is 1. Now, we have another case where our current number is a 1, and there's 2 ways to get that. All right, so the way to get that is if our number is 0 and we added a 1, or if our number is 1 and we added 0. Either way, if our number is a 1, that means our number is odd, so then we have to add 1 and divide. So when we add 1, our carry becomes 1, and we did 2 operations because we did an add and a divide. So this is carry equals 1 and 2 operations. Finally, the last case is our number is a 0. If our number is a 0, if we just did 0 plus 0, then we have no carry, and we have no, so carry is 0, and we just do a divide. And at the very end, we have to check if we have a carry or not. If we have a carry, we have to do one more operation, because like I said, if your number at the end is 1, but you have a carry, you're basically doing 1 plus 1, which will give you this, and then you have to do a divide to get the full thing. And if your carry is a 0, then you will just get this already, so you're done. So we can just return result plus carry. And so I didn't talk about this, but actually in a language like Python, you can actually get the whole number. So you can actually take this and convert it. But in most languages, when you have these like bit strings, you can't really get the whole number, because a 500, or if this is even bigger, a 500-bit number is like 2 to the 500. And you can't represent this in in like a number. You might be able to do some mod stuff. I don't think so, but maybe it's possible. Maybe you can mod your number to make it small enough and then do some operations. Like maybe that's some way to do it, but essentially you can't represent this number as like an integer or long, but in Python numbers have like unlimited length, so you can probably turn this into a number and then just do the actual operation. So you'll have some huge number, and then you could just say like, if it's odd, add 1, then divide. If it's even, divide, until basically just like while loop that, which would give you a log of the number solution, which is the same as O of n here. It would be the same exact like time complexity, because a log of the huge number will be the same as n here. So anyway, in this case, we have a O of n and O of 1. Oh yeah, I don't think we actually tried to see if it works, and it does. So there you go. So hopefully that makes sense. I would learn to play around with bits for these problems. Figure out how bit math works. Don't use the numbers themselves. Figure out like, okay, if I have bits, if I add, what happens? If I divide, what happens? What does a 1 bit represent? All these things, because this will be useful for harder problems. So definitely would get used to bit manipulation. This is like one of the easier bit manipulation problems. There's not anything too hard. So realize what happens, like, hey, if I get rid of the last bit of a number, that's equivalent as dividing it by 2. If I change the last bit of a number from a 0 to a 1, that's the same thing as adding 1. How does like adding bits work? And it's basically the same thing as decimal. So you can just think of, okay, if I have this, if I have something like this, whatever, and I'm adding these numbers, it's the same thing as adding decimal numbers, except now instead of carrying a 10, you just carry a 1. So like this would give you like a 0, carry the 1, and so on and so on and so on. It's the exact same thing. And so it's literally, if you can do integer addition, bit addition is the exact same thing. So hopefully that was helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.